Welcome to chemistry classes. In this video, we are going to discuss about haloalkanes and haloarenes. Haloalkanes and haloarenes part 3. In this video, we are going to discuss about properties of haloalkanes and haloarenes. Properties, physical properties and chemical properties. First, we can check here different physical properties of haloalkanes and haloarenes. Okay, so here first point we have to check here mainly here haloalkanes, they are colorless in pure state. In pure state, haloalkanes are colorless, but alkyl bromide and alkyl iodide, it will produce some colors when it exposed to light. Okay, here alkyl bromide and alkyl iodide, they develop color when it exposed to light. Okay, when we kept this alkyl bromide or iodide in sunlight, they develop color, but in pure state normally they are colorless. Okay, similarly here volatile halide compounds are sweet smell. Okay, volatile alkyl halide are sweet smell. Volatile alkyl halide mean alkyl halide, it can change to gaseous state or vapor state easily. Okay, so here in pure state they are colorless. Okay, but alkyl bromide and iodide, they develop color when we expose them to light. Clear? Next one we have to understand here melting and boiling point. Compared to hydrocarbon, alkyl halide, they have high melting and boiling point. We know alkyl iodide, they are polar. Okay, we discussed previous class alkyl halide. Okay, there is CX bond. Here halogens are partial negative charge and carbon partial positive charge. So alkyl halide, they are polar in nature. Because of this polarity, they have strong intermolecular force of attraction. Okay, and here compared to hydrocarbon, alkyl halide, there is halogens. Okay, so they have this alkyl halide, they contain halogens. So alkyl halide, they have higher molecular mass. Okay, because of this reason alkyl halide shows higher melting and boiling point compared to hydrocarbon. So reason here alkyl halide showing higher melting and boiling point, we discussed some reason. First reason, alkyl halide, they are polar in nature. Because of this polarity, there is strong intermolecular force of attraction in alkyl halide. Compared to hydrocarbon, alkyl halide, they have higher molecular mass because of halogen. Okay, they have higher molecular mass. Okay, so these are the reason alkyl halide showing higher melting and boiling point. So see here the order of melting and boiling point of alkyl halide, we can arrange them accordingly like this. Alkyl iodide, higher melting and boiling point compared to alkyl bromide, alkyl chloride, alkyl fluoride. So higher melting and boiling point in alkyl iodide, because the size of elements increasing accordingly. Iodine, bromine, chlorine, fluorine. This is the order of increasing size of atom. Okay, also number of electrons increasing from top to down. When we moving from fluorine to iodine, number of electrons increases. So we can say van der Waals force of attraction also increases from top to down. When you are moving from alkyl fluoride to alkyl iodide, size of atom increases, molecular mass increases. That's why they shows higher melting and boiling point. Alkyl halide shows higher melting and boiling point because of size. Another reason, when we moving from fluorine to iodine, number of electrons increases. So van der Waals force of attraction increases. Here alkyl iodide, they have higher van der Waals force of attraction because of more number of electrons. Comparatively here, alkyl fluoride, there is less van der Waals force of attraction, less number of electron. So these are the reason for increasing melting and boiling point from fluorine to iodine. Okay, size and van der Waals force of attraction. Clear? Okay, so here we discuss alkyl halide shows high melting and boiling point compared to hydrocarbon. Okay, next one we have to discuss here difference in boiling point of isomeric alkyl halide. Okay, alkyl halide produce isomer. We know what is isomer. Okay, so here look here three structures are given. Okay, they are isomers. You can see here 4 carbon. Okay, here 4 carbon, 11 hydrogen and 1 bromine atom. Okay, 4 carbon, you can check here 1 2 3 4 4 carbon and a number of hydrogen 3 6 8 9 hydrogen, not 11, 9 hydrogen and 1 bromine atom. So all this structure contain 4 carbon, 9 hydrogen and 1 bromine atom. Here this is linear structure, there is branch, also here 2 branch. So these are different structures but they have same molecular formula, so they are isomers. But you can check their boiling point here 375, 364, 346. Okay, so here this straight chain isomer shows higher boiling point. So isomers, they have same number of atoms but different structures, but they have different boiling point or different melting and boiling point. Okay, we can explain the reason for this. Okay, so here they have same molecular formula but different structure. They have different melting and boiling point. Reason for this we can explain based on their van der Waals force of attraction. You can see here the first one, chain structure. In chain structure, more charge separation possible. Okay, more charge separation possible in longer structure and their van der Waals force of attraction will be higher. Their van der Waals force of attraction will be higher. Okay, compared to these two structure, there is branch one. Branched structure means there is spherical shape. Branched structure means they have spherical shape. Spherical shape means less charge separation possible. Okay, so here you have to understand long structure mean more charge separation possible and more van der Waals force of attraction and a higher energy needed to break this bond. So long chain compound, they have high melting and boiling point. Branched molecule, they have spherical shape. Okay, so less charge separation possible and less amount of energy needed to break the bond. That's why when branch increases, melting and boiling point decreases. Clear? Also, so based on the structure we explained this. Okay, look here, this is aromatic compound, this is also isomeric form. Okay, this is dichlorobenzene, all these are dichlorobenzene. Okay, so here we have to discuss here aromatic halide, isomers. These are aromatic halide and they are isomer. Okay, these are dichlorobenzene. Look here. Here we know this is ortho position, this is meta position, para position. Okay, so here in dichlorobenzene, these are dichlorobenzene, they have almost similar melting and boiling point. Okay, they have almost similar melting and boiling point, but we can observe one difference here. Here this is boiling point. Okay, boiling point almost similar, 453, 446, 448. They have almost similar boiling point. See here melting point, when you observe melting point, here 256, 249, 323. So melting point of para isomer, okay, melting point of para isomer is big different from ortho and meta isomer. Boiling point almost similar. Okay. Also melting point of ortho and meta isomer almost similar, 256 and 249. But melting point of para isomer is big different compared to other two values. Okay. Reason for this. Here this is para isomer and this para isomer, it is symmetric in structure. They have symmetry. Okay, they are symmetric in structure, you know, symmetric structure. Okay, so they are this para isomer, it is symmetrical. Okay, so this in a given structure, this para isomer or para molecule, they can arrange very closely. Here these are unsymmetrical molecule, okay, but they are symmetrical molecule. Because of their symmetrical structure, this type of molecules can pack very closely, very closely. So they have strong intermolecular force of attraction in para isomer. To break this force, it need higher energy. That's why para isomer shows higher melting point compared to other two. So here in dichlorobenzene, ortho and meta isomer shows almost a similar melting point. Para isomer shows different melting point or higher melting point. Give reason. Reason for this you can explain. The other two isomer, they are non-symmetrical isomer, but para isomer, it is symmetrical in structure, and this molecule can close very they can pack very closely, and they have strong intermolecular force of attraction. To break this force, it need higher energy. To break this force, it need high energy. Okay, that's why para isomer shows higher melting and boiling point. Clear? Okay, next one we have to discuss here density and solubility. So we are talking here physical properties of haloalkane. We discussed their color, we discussed melting and boiling point. Next one we have to discuss solubility and density. Okay, so here first one we have to discuss here density. Here we can say density of haloalkane increases with increasing number of carbon atom. You have different haloalkane, one with a higher number, one with more number of carbon atom. Alkyl halide with more number of carbon atom shows high melting and boiling point. Okay, so here density increases with the increasing number of carbon atom. Similarly, haloalkane which contain bromide or iodide, they have higher density, okay, compared to chloride and fluoride. This compound which contain bromine and iodine, they have higher density because they have bigger size, okay, so they have high density. Also polyhaloderivatives mean hydrocarbon which contain more than one halogen, many halogen, polyhalo, okay, many halogen atom. So such type of compounds also shows high density. Okay, so generally you can say density increases with the increasing number of carbon atom. Also hydrocarbon with bromide or iodide, they have higher density. Okay, also polyhaloderivatives of hydrocarbon mean hydrocarbon which contain many halogen atom. They have high melting and they have high density. We are talking about density. They have high density. Okay, next one we have to discuss here solubility. Here haloalkanes, okay, alkyl halide or haloalkane, they are less soluble in water. Solubility in water slightly soluble, not completely soluble, slightly soluble in water, but they are soluble in organic solvent. Alkyl halide, they are soluble in organic solvent, but in water slightly soluble. Okay, so these are the things we have to discuss about physical properties of haloalkanes or haloarene. Next one, we have to talk about chemical properties. Okay, chemical reactions of haloalkanes and haloarenes. Okay, so here first one we have to discuss here chemical reactions of haloalkanes. Chemical reactions of haloalkanes we can classify three types. There are three types of chemical reactions in haloalkanes. First one, nucleophilic substitution reaction. We know what is nucleophile. Nucleophile, we will represent nucleophile like this. Okay, nucleophile mean negatively charged species. They have a strong tendency to attack on positively charged center. That is nucleophile. Cl minus, OH minus, Cn minus, these are example for nucleophile. Okay, so here first one, nucleophilic substitution reaction. Nucleophilic substitution reaction. Second one, elimination reaction. Elimination reaction. Third one, reaction with metal. So these are the three different type of chemical reactions we have to discuss here. Reactions of haloalkane. Okay, first one, nucleophilic substitution reaction, elimination reaction, reaction with metal. Okay, so here first one we can discuss here more details about nucleophilic substitution reaction. Okay, nucleophilic substitution reaction. Nucleophilic substitution reaction mean, look here, here you can see here, this is one haloalkane. Okay, here CH3, imagine here carbon with 3 hydrogen and here X mean halogen. So this is one haloalkane, it will react with the nucleophile. It will react with the nucleophile and this halogen will substitute with the nucleophile. Halogen will substitute with the nucleophile. Okay, now here it is nucleophile and X halogen is separated. This type of chemical reactions are called nucleophilic substitution reaction. Okay, so here nucleophile substitute with halogen. Here you can say nucleophile is attacking group, and X is leaving group. Okay, here halogen is leaving from this compound. Okay, and nucleophile will attack on this compound. Okay, so attacking group here, attacking group nucleophile, and leaving group halide. Clear? Okay, so here we discuss nucleophilic substitution reaction. So here some nucleophiles are given. Here some example for nucleophile: OH minus, I minus, NH3. Here NH3 there is no negative charge, but you know there is lone pair electron with a negative charge. So this is nucleophile. Cn minus, here also nitrogen with the lone pair electron, AgCN. Okay, also AgNO2, KNO2. Okay, so here there is lone pair electrons. Okay, so they are nucleophile. Different nucleophile reacted with a haloalkane gives different type of product. For example, here this is nucleophile. Okay, here NaOH or KOH, this is reagent. This reagent gives this nucleophile. OH minus reacted with the alkyl halide, it produce alcohol. Okay, so here alkyl halide reacted with the aqueous NaOH or aqueous KOH, it produce alcohol. Another one, another nucleophile, I minus, iodide. Sodium iodide gives I minus. Okay, it reacted with the alkyl halide, it giving Ri. Alkyl iodide will be formed. Okay, alkyl iodide. NH3, nitrogen with the lone pair electron, NH3, it is nucleophile. Okay, NH3, ammonia reacted with the alkyl halide, it form RNH2. RNH2 mean amine. Amine will be formed. Okay, similarly here you can remember this potassium cyanide and AgCN, silver cyanide and potassium cyanide. Okay, so here it is Cn minus, here it is AgCN. This is nucleophile. KCN, Cn minus, KCN or NaCN, here Cn minus. AgCN, here nitrogen with the lone pair electron. This is nucleophile. Also the product is different. KCN reacted with KCN or NaCN reacted with alkyl halide, it produced nitrile, RCN. Nitrile will be formed. Nitrile, RCN. Okay. Similarly, AgCN reacted with alkyl halide. Remember, AgCN it will be NC. Okay, NC, RNC, isonitrile. Okay, AgCN, RNC mean nitrile, isonitrile, alkyl isonitrile, or you can say isonitrile will be formed, AgCN. KCN it will be RCN. RCN mean it is nitrile compound. So here KCN nitrile compound, AgCN isonitrile compound. Remember this difference, different product. KCN nitrile compound, AgCN isonitrile compound. Okay. And also here one similarity, AgNO2 and KNO2. AgNO2 it will produce nitroalkane. AgNO2 produce nitroalkane. KNO2 produce alkyl nitrate. Okay, here KNO2 alkyl nitrite. Okay, but AgNO2 nitroalkane. This is RNO2 nitroalkane. RONO, we learned ambident ligand NO2 and ONO. So bonding is different. Here alkyl group bonded with nitrogen, that is nitroalkane. Here alkyl group bonded to oxygen, that is alkyl nitrate. Formula same, but bonding is different. Okay, this is already you learnt this type of bonding in coordination compound ambidentate ligand. Similarly here you can say AgNO2 nitroalkane, KNO2 alkyl nitrate. Alkyl nitrate means alkyl group bonding with the oxygen. Okay, so these are the different nucleophile and their different product. So remember this. Okay, next one we have to discuss here ambident nucleophile. Ambident nucleophile means nucleophile it contain two nucleophilic center. Okay, so nucleophile, in this nucleophile, that nucleophile bond with the carbon atom different way through different atom. Example for ambident nucleophile, Cn minus and NO3 minus. Okay, so let us check here. Cn minus, here Cn minus, here carbon bond with another carbon atom. So in such case it is called alkyl cyanide. Okay, and here nitrogen making bond, here nitrogen is nucleophilic center, then we will say isocyanide. Okay, isocyanide, RNC isocyanide, RCN alkyl cyanide. Okay, also we will say nitrile compound or isonitrile compound. Okay, isonitrile mean here RNC. We discussed before, RNC. Here carbon atom making bond with the nitrogen atom, that is isonitrile compound. RCN, here Cn, same nucleophile, here carbon making bond with another carbon atom, that is alkyl cyanide, or you can say nitrile compound, isonitrile compound, or you can say alkyl cyanide, isocyanide, that is Cn minus. Okay, so here more than one nucleophilic center. Another one, second one, NO3 minus. Here NO3 minus, it make bond through oxygen atom and nitrogen atom. Oxygen atom or nitrogen atom. Nitrogen there is lone pair electron. Okay, so this NO3 making bond through oxygen atom, then we will say alkyl nitrate. Bond through oxygen atom, alkyl nitrate. Then bond through nitrogen atom, nitroalkane. Nitroalkane, alkyl nitrite. Okay, nitroalkane mean NO3 minus, here carbon atom directly bonding with the nitrogen atom, nitroalkane, nitroalkane, you can remember like this, nitrogen nitroalkane. Okay, NO3 through oxygen, alkyl nitrate. Okay, not nitrate, not nitrite. NO3, it is nitrate, we will say nitrate. NO2 minus, this is nitrite. This is the difference. Okay, nitrite, ITE, here 2 oxygen. Nitrate, ATE, there is 3 oxygen. So these two different, okay, they are not same, nitrate and nitrite and nitrate. So here 3 oxygen atoms, so we have to say nitrate, alkyl nitrate. Alkyl nitrate mean bond through oxygen atom. Okay, nitroalkane mean carbon atom make bond through nitrogen atom. So here ambidentate nucleophile, it contain more than one nucleophilic center. Example Cn minus and NO3 minus. Cn minus, here RCN mean carbon. So carbon is the nucleophilic center. Okay, so we will say nitrile or alkyl cyanide, RCN cyanide, you can remember like this, CN, so cyanide. Okay, NC opposite, so alkyl isocyanide. Okay, alkyl, here RNC, so isonitrile, here nitrile, isonitrile, here alkyl cyanide, so alkyl isocyanide. Okay, NC, so there will be a term iso. Clear? So these are the things you have to remember about ambident nucleophile. Clear? Okay, so here we discussed nucleophilic substitution reaction. There are 2 different mechanisms for nucleophilic substitution reaction. So now we have to discuss here mechanism for nucleophilic substitution reaction. I told you there are 2 different type of mechanism, that is SN1 and the SN2 mechanism. SN1 mechanism and the SN2 mechanism. SN2 mechanism means substitution nucleophilic bimolecular. SN2 means substitution nucleophilic bimolecular. 2 represent SN2. SN means substitution nucleophilic. 2 bimolecular. Here 1 mean unimolecular. Okay, bimolecular, that is 2. 1 mean unimolecular. Okay, so substitution nucleophilic bimolecular reaction, substitution nucleophilic unimolecular reaction. These are the 2 different mechanism for nucleophilic substitution reaction. Okay, so here first we have to study more details about SN2 mechanism, substitution nucleophilic bimolecular reaction. Here SN2 mechanism always takes place, SN2 mechanism takes place in primary alkyl halide. We know there are 3 different type of alkyl halide: primary, secondary, tertiary. Primary alkyl halide mean halogen directly attached to one carbon atom. Secondary alkyl halide mean halogen attached carbon directly attached to different carbon atom. Tertiary alkyl halide mean halogen attached carbon directly attached 3 different carbon atoms, that is tertiary or 3 degree alkyl halide, tertiary alkyl halide, secondary alkyl halide, primary alkyl halide. So SN2 mechanism always takes place in primary alkyl halide. Okay. Also we learned order of reaction, first order reaction, second order reaction, third order reaction. So here you have to understand here this SN2 mechanism, it is second order reaction. Second order of reaction is second. It takes place always in primary alkyl halide. Okay, and this chemical reaction always takes place in presence of aqueous sodium hydroxide, aqueous NaOH or aqueous KOH. We know NaOH or KOH, it provide nucleophile OH minus. OH minus is the nucleophile. NaOH or KOH, it provide nucleophile OH minus. Okay, so here alkyl halide, primary alkyl halide reacted with aqueous NaOH or KOH, the product will be alcohol. Alcohol will be the product, and this chemical reaction is second order reaction. Okay, here it is second order reaction, mean here rate of reaction depends on the concentration of alkyl halide. Also it depends on aqueous OH minus. Okay, so SN2 mechanism, it is second order reaction, mean rate of reaction depends on the concentration of alkyl halide. Also it depends on the concentration of nucleophile. That's why this chemical reaction is second order reaction. Okay, so look here, this is one primary alkyl halide, CH3Cl. Okay, so look here, we know nucleophile, it is negatively charged particle, so it will attack carbon atom from this backside direction, because here already negatively charged chlorine. So OH minus cannot come this direction, because this two negative charge, there will be repulsion. Okay, that's why this OH minus will attack this positively charged carbon from this direction. Okay, then there will be a short-lived intermediate product. Okay, after that this is the final product. Okay, final product here, this is methanol, alcohol is formed. So look here, here the product formed with the inverse configuration, invert configuration will be invert. Okay, look here its configuration like this. Here chlorine, halogen in right hand side. Okay, finally here nucleophile here in left hand side. So here a product during SN2 mechanism, a product formed with inverse configuration. Okay, so here we discuss mechanism for nucleophilic substitution reaction. There are two mechanisms, SN1 and SN2. Okay, and here we discuss more details about SN2 mechanism. SN2 mechanism happen only in primary alkyl halide. Okay, and here primary alkyl halide undergo nucleophilic substitution reaction in presence of aqueous OH minus, nucleophile OH minus, and here product is alcohol. Product formed alcohol. Alcohol is the product. And this is second order reaction. This is second order reaction. Why it is second order reaction? Because rate of reaction depends on the concentration of nucleophile, also concentration of alkyl halide. Okay, this is the reason. Okay, and here product is alcohol and a product formed with the inverse configuration. Clear? These are the things you have to remember here. Okay, so here we discussed SN2 mechanism. Okay, so here in SN2 mechanism, nucleophile approach on positively charged carbon atom. There must be an approach. There must be an approach of nucleophile on carbon atom. Okay, if there is any bulky group on the carbon atom, if there is any bulky group, what do you mean by bulky group? Bulky group means, see here, this is one alkyl halide, simple alkyl halide, and this is tertiary alkyl halide. This is chlorine attached carbon, this is positively charged carbon, and this nucleophile will approach on this carbon atom. There are three bulky groups, CH3, 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 bulky group. But here simple hydrogen atom only hydrogen atom. So this is simple alkyl halide. If there is any bulky group, this type of bulky group on carbon atom or near carbon atom, this bulky group produce an inhibition effect. Okay, so here this type of bulky group prevent the approach of nucleophile on carbon atom. Okay, it will prevent. They make a barrier between nucleophile and the carbon atom. Okay, that's why this type of reaction will be slow. If there is any bulky group near carbon or on the carbon atom, the reaction will be slow. But look here, this is primary alkyl halide. Primary alkyl halide mean halogen attached carbon, there is only hydrogen atom, or sometimes there is one carbon and two hydrogen atom. Okay, so here nucleophile can approach carbon atom very easily, comparatively very less inhibition effect. There is very less inhibition effect here, so here reaction will be faster. But this type of tertiary alkyl halide or secondary alkyl halide, there is bulky group. Okay, so reaction will be slow because nucleophile cannot approach positively charged carbon atom easily. Okay, so we can arrange alkyl halide according to their speed of chemical reaction. Look here, SN2 mechanism will be faster in primary alkyl halide, then secondary alkyl halide, then tertiary alkyl halide, because here in tertiary and secondary there is bulky group and they produce an inhibition effect. Also you can check this diagram here, and this diagram help you to understand this one. Okay, so here we discuss SN2 mechanism we discussed. Next one we have to discuss here SN1 mechanism, nucleophilic substitution unimolecular reaction, that is SN1 mechanism. Tertiary alkyl halide involved in SN1 mechanism, we already discussed SN2 mechanism. Primary alkyl halide involved SN2 mechanism and to produce alcohol, primary alcohol. Primary alkyl halide, primary alcohol. Okay, it is second order reaction. SN2 mechanism, it is second order reaction. That's why it is called the SN2. Next one, SN1 mechanism. SN1 mechanism mean it is first order reaction. Okay, first order reaction. That's why it is called the SN1 reaction. Order of reaction 1. Order of reaction 1 mean here rate of reaction depends only reactant and do not depends on the concentration of OH minus. Okay, and I told you here SN1 mechanism, here this chemical reaction tertiary alkyl halide. Tertiary alkyl halide mainly involved in SN1 mechanism and it produce tertiary alcohol. Also you have to remember this SN1 chemical reaction, SN1 mechanism happen in presence of protic solvent. Protic solvent mean there will be solvents such as water, alcohol, acetic acid. Okay, so here solvent, sodium hydroxide must be dissolved in water or alcohol or acetic acid. Okay, mainly here we will say alcoholic NaOH or alcoholic KOH reacted with tertiary alkyl halide, it produces tertiary alcohol, and this is SN1 mechanism. Okay, so here tertiary alkyl halide, tertiary alcohol formed. Okay, and see here, this is, I told you this is first order reaction because rate of reaction depends on tertiary alkyl halide, do not depends on the concentration of OH minus. Okay, so look here, this is one example for this type of chemical reaction. You know, this is tertiary alkyl halide, halogen attached to the carbon, directly attached 1, 2, 3, tertiary 3 carbon atom. That's why this is tertiary alkyl halide. Tertiary alkyl halide reacted with OH minus, it produced tertiary alcohol. It is SN1 mechanism. This SN1 mechanism takes place in 2 steps. SN1 chemical reaction takes place in 2 steps. This is first step, this is second step. In first step, tertiary alkyl halide changes to tertiary carbocations. What do you mean by carbocations? You learned in grade 11 carbocations means CH3, CH2 plus, okay, CH3, CH3 plus. Okay, so here hydrocarbon with a positively charged, this is carbocations. Okay, so here this is tertiary alkyl halide reacted with OH minus, it produced tertiary alcohol. It is SN1 mechanism. Okay, and this chemical reaction takes place in 2 steps. First step, here tertiary alkyl halide changes to tertiary carbocation. Okay, here this one you can draw like this, one carbon atom. Okay, here CH3, here CH3, here it was halogen removed, then there is positive charge. So this is tertiary carbocation formed. Then second step, this is second step. In second step, tertiary carbocation reacted with OH minus, it produced tertiary alcohol. Okay, so here first step, this is very slow step, slow reaction. Okay, also this is reversible reaction. Okay, in chemical kinetics we learned in organic chemistry, if there is multiple step, the slow step is the rate determining step. In chemical kinetics we discussed in organic chemical reaction, some organic chemical reaction takes place in multiple steps, more than one step. Okay, for example this one, this chemical reaction takes place more than one step. This is one step, this is second step, so there is more than one step. Okay, so this is slow step and this is fast reaction. This is slow reaction, this is fast reaction. If there is more than one step, so the slowest reaction always rate determining step. Okay, so here this is the slow step and this is rate determining step. And you can see in this chemical reaction only alkyl halide, okay, only reactant. So that's why this is first order reaction. Okay. Also here you have to understand, during this chemical reaction tertiary carbocation formed. Tertiary carbocation, we know there are different type of carbocation. Primary carbocation, secondary, this is primary carbocation, this is secondary carbocation, this is tertiary carbocation. In grade 11 we learned tertiary carbocation more stable than secondary carbocation than primary carbocation. You can revise grade 11 organic chemistry once again, then you can check back this. Okay, so here tertiary carbocation is more stable than secondary carbocation than primary carbocation. Okay, so here tertiary carbocation is more stable. That's why this chemical reaction takes place faster. Okay, so this chemical reaction takes place faster. Okay, if there is secondary, look here, imagine secondary alkyl halide and primary alkyl halide. You have 3 alkyl halide, primary alkyl halide, secondary alkyl halide, tertiary alkyl halide. All this separately you reacting with OH minus. So which product formed faster? Tertiary alkyl halide produced tertiary alcohol faster. Okay, and another 2 reaction will be very slow. Why this like this? Because tertiary carbocation is more stable and it formed faster. That's why this chemical reaction takes place faster. But other 2, secondary and primary, the chemical reaction will be slow. So SN1 mechanism, we can arrange their order of reactivity. Tertiary alkyl halide rate of SN1 reaction will be faster than SN2 reaction, then SN1 mechanism faster in tertiary, then secondary, then primary. Primary alkyl halide SN1 mechanism reaction is very slow because primary carbocation very less stable. Okay, so here rate of this reaction depends on the stability of carbocation. Okay, tertiary carbocation more stable, that's why this reaction is faster. So here we discussed nucleophilic substitution unimolecular reaction SN1 reaction. It will take place in tertiary alkyl halide and product will be tertiary alcohol. Okay, and the order of reactivity like this: tertiary, secondary, primary, because tertiary carbocation during this chemical reaction carbocation is formed, tertiary carbocation is more stable, that's why tertiary alkyl halide chemical reaction SN1 reaction is faster. Also we discussed this is first order reaction. Okay, this is first order reaction. These are the things we have to discuss, we have to remember here. Clear? Next one we have to discuss here SN1 mechanism in allylic halide and benzylic halide. SN1 mechanism in allylic halide and benzylic halide is very faster. Okay, comparatively faster reaction because this allylic halide and benzylic halide they produce resonance structure. Okay, that's why they are producing resonance structure. That's why this type of chemical reaction SN1 reaction in allylic halide and benzylic halide are faster. Okay, this is allylic halide. You know allylic halide, we learned classification of alkyl halide, allylic halide, benzylic halide we discussed already. So this is allylic halide, this is benzylic halide. They produce resonance structure. Grade 11 you learned grade 11 resonance structure. So look here, this double bond shift over here and this structure became like this here, double bond. Okay, so here double bond shift over here and they form resonance structure. Okay, and see here there is the shift of positive charge and here this double bond shift over here and positive charge came here. Okay, look here, and again this double bond shift over here and positive charge came here. Okay, this type of resonance structure happened in benzylic. This is benzylic halide and this is allylic halide. So here you have to understand SN1 mechanism in allylic halide and benzylic halide are faster. Give reason. The reason for this, they produce resonance structure. Okay. Also you remember here SN1 mechanism and the SN2 mechanism faster in alkyl iodide, then alkyl bromide, then alkyl chloride and alkyl fluoride. Rate of reaction very slow in alkyl fluoride, then faster in alkyl iodide. Why rate of reaction or order of reactivity like this? Because we know size of halogen increases from top to down. From fluorine to iodine, size of the element increases. So iodine bigger size. Okay, so here we know carbon iodine bond. So bond length mean if the size of atom is bigger, so bond length will be higher. Okay, bond length in carbon iodine, bond length is higher because iodine bigger size. So bond length is higher mean less energy needed to break this bond. So alkyl iodide faster reaction. But comparatively fluorine or chlorine size is smaller. Okay, so bond length is smaller, so more energy needed to break this bond and rate of reaction slow in fluoride and iodide. Okay, so this is the order of reactivity: alkyl iodide faster reaction, alkyl fluoride slow reaction. Clear? So here we discuss allylic halide and benzylic halide produce faster SN1 mechanism because they produce resonance structure. Clear? So these are the things we have to discuss in this video. So here in this video we discuss physical properties of alkyl halide, Then we discuss chemical properties of alkyl halide. So in chemical properties of alkyl halide, we discussed only nucleophilic substitution reaction we discussed. In nucleophilic substitution reaction, there is SN1 mechanism and the SN2 mechanism. Okay, so there is elimination reaction and reaction with metal. In chemical properties of alkyl halide, we said there are 3 chemical reactions. Okay, out of 3 we discussed only 1, so rest of 2 we will discuss next video. Okay, so thank you for watching this channel.